All right, I digress. Sorry to start so late. Oh my goodness, it's really late. I'm so sorry. I'll begin with a word of prayer. Dear Father, we thank you for this day. I thank you for these students and their patience, and just help us to understand a little bit about connectedness today, Lord. In your name I pray. Amen. So, connectedness. Connectedness is a major topic in topology, right? So let's give the definition. And it does kind of, it is more or less what it sounds like. I mean, we have some sort of, default intuitive idea about what connectedness is, and just in terms of English language, and or maybe not just also Vietnamese, right? Is there I mean, you guys also have connected, right? It's not like an exclusively English concept. I mean, there's some kind of word for things being connected, not in a mathematical sense, but in sort of a common everyday sense in Vietnam, right? Yeah, like you could talk about like closely connected relatives, or something like that. So here it is. Well, he starts out with this discussion about making a new topological space from a pair of topological spaces, right? So did I talk about disjoint union? I'm trying to remember which book that was in. There's a specific construction that's really simple. I can't remember where I found that, if it was in Gamelin or if it was in something else I was reading. Oh, is that in here? Is that one of the things that he had in here? Oh, yeah. So this is from, Topology by Klaus Janik, I guess. And here's his definition: disjoint union of sets. He uses x plus y, and his definition is that this is equal to x Cartesian product with 0 unioned with y Cartesian product with 1. He says we immediately start treating x and y as subsets of x disjoint union y in the obvious way. Like, how do you identify a copy of x inside here? X is included into what? Like this, right? And y, we think of y as this inside that space, right? I mean, so I think another notation you'll see sometimes for this is like I'm pretty sure I've seen this in other books. Disjoint union, right? Yeah. Like an upside down pie kind of. Yeah. Here's the difference. If you had, what's R union R? It's R, right? But R disjoint union R is not equal to R. The disjoint union of R and R is also not R2. All right, one of the ways I can see that R disjoint union R is not R2 is that topologically they're distinct. See, because R2 is actually connected. In fact, it's path connected. Whereas the disjoint union of R and R is in fact disconnected. So I think that was kind of interesting. That's his starting point in Gaiman, is to talk about connectedness. He's like, if a space is disconnected, that means in some sense you could like break it into a disjoint union. I think he's looking at it in a kind of pragmatic way. Disconnectedness means that in some sense you could take your topological space and you could break it into a disjoint union. Or at least it would be homeomorphic to a disjoint union, right? If not directly a disjoint union. So when is it possible to do that? When is it not possible to do that? When it's not possible to do that, the set is said to be connected. But we can be more specific than that, right? So, definition, topological space X is connected if X cannot be expressed as a disjoint union of two non-empty sets and he says which are both open and closed, but I don't remember that as being the definition in other places. The definition I remember is as follows. And maybe this is an automatic consequence of my definition, so it's like it's not really, we don't really disagree, but as I recall, the definition of connected is X is connected topological space if and only if there does not exist U and V open such that U union V is X and U intersect V is empty, which is to say that X is connected if and only if it cannot be written as the union of two disjoint open sets. And by the way, everything I just wrote here, the existence of open sets that union to the whole space and intersect to be empty, this is said to be a separation of X.
Refill your definition.
Does it matter? Are these equivalent? I'm asking. Disjoint union means U intersect V is empty, right? So my question is, I think it's equivalent, right? Because given this data, what's the complement? It's kind of silly, right? What's X complemented by U, given the data here? It's V, right, by set theory here, and vice versa, right? So we don't really disagree, because if U and V are open, then their complements are open, which means that they're also closed. What would the homeomorphism to a disjoint, disjoint, dang it. Well, now I'm using disjoint union in two different ways. Here, I was using disjoint union as an honest-to-goodness union in the set theoretic sense, right? But there's also the formal constructive disjoint union as put forth by Yannick over there. And so like if I had X is a disjoint union in the ordinary set theoretic sense, what would that be? What would the homeomorphism be to, let's say, U box V? Here's how you define it. F of x equals to, well, x, Cartesian, oh, poor choice of variable. Let's say z. Z, Cartesian, what was it? Zero. I guess let me use the notation z0 if z is where? Yeah. Is where? In U. Yeah, it's debatable, right? And it's z1 if z is where? If z is in V. And so it should be relatively simple to show that that is a homeomorphism with respect to the natural topology that you put on these different spaces. Yes, what should the topology be on the disjoint union is the question, right? I think it should just be the open sets that are already there for U and V from X with 0 or 1 slapped onto them. Given that, it's clear that that's, in fact, a one-to-one and continuous map with continuous inverse. So anyway, this is like a formal, I'm just telling you this because at times in my life, people have said to me, take the disjoint union, and I didn't know what that meant. Because they told me to take the disjoint union of R and R, and that just blew my mind because R union R is R. What do you mean take the disjoint union of a set in itself? Well, it's a construction, all right? It's a way of getting two copies of R which you're thinking of as formally distinct. And this is just one way of doing it. There are probably other ways to form the disjoint union. This is just like a construction of it, okay? But anyway, a topological space is connected if it is not homeomorphic to the disjoint union of two subsets. Which also literally means it's not the set theoretic disjoint union in this context. Okay, now that I got that out of my system, what's next? So theorem, let F be continuous from a connected topological space to a topological space Y. So we're not assuming Y is connected, we're just assuming that's connected. Then the image is connected. So in other words, the continuous image of a connected set is connected. So how would you prove such a claim? Let me draw a picture. So here's my X, right? Over here is my image, F of X, right? Suppose you had a separation, right, of the image. Suppose you had a separation. Suppose you could break it up into a U here and a V here such that U union V is the entire image and, you know, it was disjoint. Then what would happen when you take the inverse image of that? So of course that's all of X, right? Because X is F inverse of F of X, right? The inverse image of the whole image is the whole domain, which is X. And yet, the inverse image of the union of U and V is what? It's the union of the inverse images, right? But what do we know about the inverse image of open sets? What's that? They're open, right? Because F is what? Continuous. So this is open. That is open. Well, that covers the domain. Is it a separation of the domain? Why? Why is that a separation of the domain? Right. So, I mean, we could just do it through direct. If we knew enough properties of inverse images of functions, we could just appeal to those properties, right? Like the yeah, that's my question. Is what? How does inverse image work with intersection? Say again? Preserves the operation. Yes, but my question is that the inverse, is that the intersection of the inverse images? Okay. Say that again?
His definition allows you to just find any proper subset of X that is both closed and open and not equal to the empty set, and that gives you connectedness without finding another one.
Disconnectedness.
Yes, yeah.
Ah, so very, very good point.
But that idea makes that theorem a little bit easier to prove just because you're only looking at one set in the image as opposed to two.
Oh yeah, but we're almost done.
Yeah.
So this is the empty set. So you're looking at his proof?
Yeah.
Yeah. Yeah, like you said, his proof is based on finding one set in the domain which is both open and closed. If there is one set, if there's one set in the image which is both open and closed, then that will give you another set in the domain which is both open and closed, which then contradicts the connectedness of X.
Yeah.
I'm at the moment trying to explicitly construct a separation of X to get a contradiction. And I think we've got that because the inverse image of the empty set is the empty set, right? And so that means that this is a separation of the domain, which contradicts the fact that X is connected. Which means that there does not exist a separation of the image. Which means that the image is connected. Do you guys want me to go through the proof in Gamelin here? No? Okay. All right. So next up. Next up. Theorem 8.2. we've got a family of connected subsets. Connected family, rather, of, good grief, family of connected subsets of topological space X, all right, such that, E alpha intersect E beta is non-empty for each distinct pair of indices alpha and beta in the index set lambda, then guess what? Right, then the union, you say countable? No, okay. I just hearing things. Yeah, there's no countability here, right? I mean, there's no accountability. Say again, the what? Oh, it could be countable. It just doesn't have to be. Okay, okay. Yeah. Then this is connected. So that's kind of reassuring, right? I mean, you can kind of picture it, right? If there's always some kind of intersection, you know, between any pair of these, it makes sense that the union would be connected.
This theorem is a little less strong than that, right? Because this is saying that every pair has to have some common elements between every other set. Or like every subset has to have a common element with every other subset.
Oh, no, it's not like a bouquet. It's just that for distinct. Oh.
I was thinking the same thing.
Oh, you're right. My picture's not right. It's more horrible. It's more like this, right?
Yeah.
So there's a common intersection between any two.
I feel like you could extend the theorem and try and like index the subsets or something like that, and then say that if you had common elements between every successive subset, then that would give you kind of that chain-like thing.
Well, I don't know. I know that I can prove this for path-connected spaces. There's a nice argument there. So your question is, can theorem 18? Can we just assume that? How to say that?
Yeah, it is tough to say. Because you can't say something like for every subset there's a distinct subset such that they have common elements, because then you could have like two subsets touching each other and another two that are touching each other but apart. So I don't know how to say it.
You have to like put some kind of ordering
Right.
on the indices such that that ordering transfers to the connectedness of the connected. Yeah. Oh, well, I've become disinterested in this theorem. Can we go on? I mean, we could prove it. Shall we try? How's it go? Oh, I guess it's good for me to go through the proof because it forces me to appreciate his definition, right? So what's the proof look like? Yeah, so this picture is not enough for this context. And I don't know off the top of my head, Jonathan, if we deal with the class of just connected spaces as opposed to path connected, if that actually doesn't, if it's not actually true. If you could then restrict it furthermore to the set of, to the context where the index set had some interpretation which allowed the natural, that allowed us to formulate the theorem that we have in our mind. Proof. Sorry. He says E equal the union of E alpha. All right. We're trying to prove that that's connected, right? And let F be a subset of E, both open and closed. What's that mean then? What's he mean? Replacing F by E complement F if necessary, we can assume that F is non-empty. Oh, I get it. If F is empty, its complement is non-empty. And it's also open and closed. So without loss of generality, we can assume F is non-empty, right? Because if it was empty, then its complement is non-empty, so you could let that play the role of the non-empty open and closed set. All right, so it suffices to show F equals to E. All right, so what's he do? He says let X be an F, then what? Well, it's got to be somewhere, right? So X is an element of E of, he calls it alpha naught. Since F intersect E alpha naught is non-empty, and what else about it? He says it's a non-empty closed and open subset of E alpha naught. Why is that? I'll do the easy part. Why is it open? Because we're taking the intersection of F, which is open, and E alpha naught, which is assumed to be open, right? Intersection of two open sets is open. Why is it closed? Why is this closed? Why is that closed? What do you do to see if something's closed? Take the complement, right? So we look at X complement by F intersect E naught. What's that look like? I believe that's equal to X with F removed, unioned with X with this removed, right? De Morgan's law? The complement by the intersection is the union of the complements. But closed, hence open. F is closed, so the complement's open. And how about this one? Oh, that's closed?
Yeah, so we showed that it's open and now X complement F is both closed and open.
Oh, this one I'm okay with. It's You're saying this is open?
I'm saying that's open and closed, right? Because F is both open and closed.
I suppose that's also true, yes. But I'm mostly interested in showing that this is open because that will prove that that's closed.
Oh, yeah, right.
There are many things which are true. I'd like to see why that's open. Hmm. Yeah, I know that E alpha is a connected subset. I mean, he says in this proof that F intersect E alpha naught.
Oh, it's a non-empty closed and open subset of
Oh, he says.
E sub alpha not, right? So isn't E sub alpha not necessarily closed and open? Because that's our universe.
I'm sorry?
What universe are we looking at when he says that F intersect E sub alpha naught is closed and open? Like closed and open in what?
I thought we were just talking about the topology of X here. I don't think there's any relative topology going on here. He says, since F intersect alpha E naught, E sub alpha E naught is a non-empty closed and open subset of alpha E naught. Okay, so you guys are on the right. You're on the right hunt. So I think to help drive that home, this is a subset of E alpha naught, right? That is connected, and so to say that that's connected, you're right. That is a statement about relative topology. That you're right. Yeah. And so then what? Oh, so if this,
wherever the case, then we can intersect wherever it goes. And you have open closed with respect to the relative topology.
I still don't see why that. Why is this both open and closed?
I mean, in the relative topology.
Of E alpha naught.
Yeah.
Why is it closed?
Because F is closed, so the intersection with respect. What I'm talking about is the relative topology, not the topology outside.
Why is F closed in the relative topology?
Because you have a intersection of closed and the space.
So you're saying that if I have A and I have V closed, then this right here is automatically closed?
But not the empty space. Not necessarily. It's just closed in the relative.
If that's true, then I agree with you. That's true? I already said that a previous day and I've forgotten it, right? Yeah, probably. Do you guys, does that make sense to you guys? I mean, I think that would be a decent problem to work out if you don't believe it. Given that V is closed, What's that mean? V being closed in X means that the complement of V, everything outside of V, is open. So if we intersect the complement of V with A, we get everything else in A being an open set, which then means that the complement of the hatched region is open in A, which is to say that the hatched region is closed in A. So King is correct. I mean, so with that theorem, then it implies that F being closed in X implies F is closed in E sub alpha naught. And then what?
I think that's it, right? Because we're saying that F intersect E sub alpha naught is closed. So now we have.
Oh, right. Okay, yes. So that's closed and it's open. Therefore, it must. Therefore, F intersect E alpha naught is equal to F is equal to E alpha naught, right? Because this is a subset of E alpha naught, which is both open and closed, and because E alpha naught is connected, it must be the whole set. Now the next part of the proof is, moreover, if beta is any index, then F intersect E beta is an open and is an open, closed and open subset of E beta that includes E alpha naught. All right, so let beta be in lambda any beta. Then F intersect E beta is a subset of E beta, right? Both open and closed, right? Because again, F is same logic, right? What's that say? So therefore, F intersect E beta is equal to E beta, right? And of course, E alpha naught intersect E beta is a subset of E beta, right? And he says,
Yeah, by assumption, E sub alpha naught intersect E sub beta can't be the empty set.
right. I've somehow not said that. Ah. All right. So I guess that, I need this to get that therefore, because otherwise it could just be the empty set. The words. Anyway, to complete it, so F intersect E beta must be all of E beta, and F is a subset, F contains E beta. Since this occurs for all beta, F is equal to E, which is what we wanted to show. Anyway, I'm going to move on. I need to get to the path connected where I feel like I'm saying something that makes sense. Almost every example I'm interested in is path connected. I miss path connectedness. All right. If I had any common sense, I wouldn't have started the proof of that today. All right. This is important, though. Let X be a topological space. all right, and X be an element, then the connected component of X, denoted CX, is the union of all connected subsets of X which contain, let me call that X sub naught so you can see the difference, X sub naught. There we go. Why is that connected? Right. So they all meet at X naught. Right. So that sort of maximally overlapping condition in the theorem is met because they're all containing that X naught point. By theorem 8.2, Cx is connected, and it is evidently the largest connected subset of X which contains X. He says, suppose E is a connected subset of X that meets C of X, then E union, so, if E is connected, right, and E intersect Cx is non-empty, then E union Cx is connected with, I tell you. If he is, I'm not saying this clearly. It has to be a subset of Cx is kind of the point here, right? What's that? Oh. You're right. It just meets C of X, so the condition is E intersect C X naught, non-empty. Let me see here. In other words, what he says is E union C of X then has to be a subset of CX. He says, in particular, if C of Y is the connected component of another point, Y and X, then you got two possibilities. Either Y is in CX, or I'm sorry, I can't. All right, picture. So here's my X naught, right? Here's C of X naught, the connected component containing X naught. You pick another Y in the space, right? Right, and you can look at the connected component of Y. So if the connected component of Y meets the connected component of X naught, right? If this intersect C of X naught is non-empty, then in fact they have to be equal. On the other hand, so they either match or they're disjoint. Those are your choices. And that's why these are called path components. Connected components. I've got path connectedness on the brain. Let me, one step at a time here. All right. That's theorem 8.3. The two connected components of X either coincide or are disjoint. All right? And the connected components of X form a partition of X into maximally connected subsets. So you can kind of take a topological space and chop it up into disconnected pieces. I mean, the connected component is connected, among other things, okay, right? So a picture is, roughly speaking, something like this. Not a great picture, but, you know, there are different... They obviously do not have to, in principle, be, you know, there doesn't have to be a finite number of them. I'm sure you could have an uncountably infinite number of path components for some sort of example, if you were so desiring of it. Other spaces have one. I just said path again. We don't know what that is. Connected component. So you could have a finite number, but the larger point is that they're disjoint, right? They're disjoint, and the union of them covers the whole space, right? So these are a partition of the topological space, the connected components. All right. This theorem is harder than anything else we've done today. I'm not even going to try to prove this. And besides, this is really the province of real analysis. Any interval closed, open, semi-open, finite or infinite. Guess what? In R is connected. Theorem 8.4. So this actually has relevance to calculus, all right? Why does this matter to calculus? What's that? Exactly, the intermediate value theorem. So if we look at f, say from the closed interval a to b, right? You know, to the reals, then this is a connected subset, right? If that's continuous, that means if you look over at the range, if you put, you know, if f of a is down here, and if f of b is up here, and if you got any n in between those, it has to be in the image. Of course, this is the intermediate value theorem. It's a consequence of this theorem that the connected image of a connected set is connected, and the fact that intervals are a connected subset of reals. Right, these are the only possible connected subsets of the reals. Yeah. There are 9 types. Closed, open, clopen, opposed, and then the raised to infinity, either including or not including, to either plus infinity or minus infinity. That's 8. What's the remaining one? What's that? Yes, a point. A singleton is connected. You can't separate a point from itself, right? Like, what if you got a really sharp knife? It's like, you cannot cut a point. No.
So this theorem can be generalized to R to the n, correct?
Yeah, I mean, well, the question is, what are the connected subsets of R to the n? Yeah, exactly. I also think about three-dimensional blobs, but you could also have like a three-dimensional blob with like a filament over to another three-dimensional blob, or a whole network of those, and they'd still be connected. Because path connected implies connected. What is path connected? Now, if you want to think more about this, I think I posted you guys links to my brother's. My brother's written a couple of papers with some of his colleagues at Appalachian State, and did you read those?
Yes.
Were they helpful?
Yes. That was like the only one I read. I don't understand anything in that one.
Oh, this one? Yeah. Well, that's the thing is I think, well, that's my brother's target audience is like future teachers, people who are teaching like calculus in high school, trying to get them to understand that there are parts of calculus which are intrinsically topological. Intermediate value theorem is one of the principal things. The extreme value theorem is another one because that has to do with the compact image of a compact set being compact in terms of bounded, yeah. So if you have, what I'm trying to say is if you haven't read those already, it might be a good time to do it because it might give you deeper intuition without getting stuck in the esoteric details of, it'd be relaxing to read his paper at this point in your life is what I'm trying to say. I should read his paper.
Well, the test about the like, things in that paper rather than these things.
Let's see here. Path connectedness. So what is path connectedness? So, what's a path? Gamma from 0, 1 into x, continuous, with gamma of 0 equal to x naught, and gamma of 1 equal to x1 is a path from x naught to x1. What does it mean for a space to be path connected? X, a topological, X is a topological space. Let me not write it again. X is path connected if what? If for any pair x, y, and x, there exists a path in x connecting x and y. Path in x from x to y. Before I get sucked into his theory, let's prove Rn is path connected. I pick 2 points. Let me call them P and Q. All right? I will now construct the path from P to Q. Behold, gamma of T is P plus T times Q minus P. There you go. That is a path from P to Q, with gamma of 0 being P and gamma of 1 being Q. So you didn't realize it, but in Calculus 3, I was working on showing you that Rn was path connected. Like every time we start talking about parametrized line segments, that's the proof of path connectedness of Rn. Right? And with this in hand, you could do other things, like prove a ball is path connected. What if you wanted to prove a ball was path connected? Could you do it? Let's look at the disk of radius r centered at x naught, a subset of metric space x. Oh, x with norm. Can you prove that the and here I mean here's the definition for that, guys. I mean, I'm not sure. I don't know if this definition is in game one. It's just a notation I've been using. I forget where it started. So can we prove that that space is path connected? I mean, I think we can use the same trick, but then what was not an issue for this was what?
You don't have to show that all the points in between are in Rn.
Right, it's just manifest that this formula is still in Rn, right? There's no danger. Only a truly crazy person would be like, I'm not sure that's an n vector, right? But it's a legit complaint if, if P and Q are in the disk of radius r centered at x naught, then yeah, we can define gamma of t the same way we have. But then the question becomes, why is the norm of gamma of t, why is that minus x naught less than or equal to r? For 0 less than or equal to t less than or equal to 1. See, there I'd actually have to do some calculation to show that that's true. Right? And then there are more adventurous examples, right? That you can see, right? You can see that this space is path connected. I mean, you can just see it. But to actually construct the path, well, it depends on what your standards of proof are, right? If you'll allow me a proof by picture, if proof by picture works, then I pick 2 arbitrary points, and I'm like, la 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 la. There we go. And then you have to believe me that I can make the domain of that 0 to 1, right? By appropriately speeding up or slowing down the path. You can always adjust the length of the domain to 0, 1, right? Starts to feel less like a proof, right? So maybe, depending on how picky you are, you got more work to do there. Of course, I didn't tell you where this annulus is sitting, but you get the idea. Now, okay, so some examples aside, path connectedness is an equivalence relation on points. So like, in other words, I'm saying is we can say x is equivalent to y if and only if there exists gamma such that what? Gamma goes from x to y, right? So my claim is that if you define x equivalent to y like this, that is in fact an equivalence relation. Can you prove any point is equivalent to itself? Like, is it reflexive? Is a point equivalent to itself? What's the path that goes from x to x? What's that? The identity, right, yeah. If we just let gamma of t equal to x, then gamma of 0 equal to x equals to gamma of 1, and you can prove that that mapping is continuous. What next?